Okay, in this video I want to talk about maxima and minima, local maxima and minima for a function of two variables. Okay, so in this situation here I've got z as a function of x and y, and I'm going to say it's twice continuously differentiable in some open region of the xy plane. Okay, now you remember we've done this previously. Okay, remember how I wrote z equals f of xy as a level surface? I did the following. I played the following trick. I just subtracted z on both sides of the equation above, and I get little f sub xy minus z. And since that's a function of x, y, and z now, I am calling that cap f of x, y, and z. Okay. So there we've got a function of x, y, and z. Now the gradient of cap f, which I've written here, would be what? We've already gone through this. Little f sub x, comma, little f sub y, comma, -1. We know that's going to be normal to the surface at each point. Now at an extreme value, or an extrema, okay? I should say extremum. The extrema is the plural. Extremum is the singular in Latin here. So that means what? A minimum value for z or a maximum value for z. Okay, so you can think of if z is a nice, smooth surface, then I'm talking about what the peaks and the valleys, the high points, the low points on the surface. Okay, those are the extrema. Okay. At an extremum, the tangent plane should be parallel to the xy plane. Okay, does that make sense? All right. So if you're at the high point on a hill, okay, at the very high point on the hill, you've got a tangent plane to that high point being parallel to the xy plane. Okay, parallel to the xy plane. Any normal then would have a k component only. Okay, does that make sense? Any plane that's parallel to the xy plane will have a normal which is a multiple of k. We'll have a normal that is k, actually, but any multiple of k, non-zero multiple of k, would also be a normal. Okay, so I will say have a k component only. So wait, if this is normal to my surface at each point, the gradient of f, for the extrema then, the I and j components should be what? Should be 0. Okay? So that means f sub x should be 0 and f sub y should be 0 at the extremum. Okay? Notice there is a k component left. Okay? As expected. Okay? As a shorthand, notice that the gradient of little f, come up here to my original. I was originally just dealing with little f, and said z is equal to little f, and then introduced this cap f thing. But let's go back to little f now. The gradient of little f would be what? F sub x, comma, f sub y, right? In angled brackets. Okay? Saying these are both 0 more compactly could be just saying the gradient then is the what? 0 vector. See the bar on top of that 0. Okay? So at any extremum, then the gradient of little f should be the 0 vector. Okay? The converse need not be true. Okay? This should remind you a little bit of what happened in, more than a little bit, what happened in Calc 1. Remember in Calc 1 where you were doing what? You were taking, to find extrema, local maxima or minima, you were doing what? You were taking derivatives of the function and setting it to 0. Okay, but do you remember that sometimes you could have points, for example, points of inflection, where the derivative was 0, but it was neither a minimum nor a maximum? Well, the same thing's going to happen in this situation here. So I say here the converse need not be true. So let's take a concrete example, though. Find the potential extrema of little f of xy is x squared plus 4y squared minus 2x plus 8y minus 1. Okay, so if I went z equals f of xy, this would give us a nice, what, quadric surface. Okay, Let's go ahead and compute the gradient of little f, and that would be what? 2x minus 2, 8y plus 8. And if I was to set that equal to the 0 vector, then what I've got to do is what? Go 2x minus 2 equals 0. That implies y is equal to 1. 8y plus 8 is 0. That implies y is negative 1. And I have the point 1, negative 1 as a potential extrema. Extremum, I should say. Okay, apparently there would only be one. Can you tell me what kind of quadric surface this would end up being, by the way? Okay, all right, give a little thought to that here. All right, now what I do want to mention here, let's come up here before I look at anything else. When you're in this situation here, now this was a fairly easy function of x and y. But if the function of x and y is a little bit more gnarly here, you could imagine that these functions, f sub x and f sub y, are functions of both x and y, and you're setting that equal to 0 so that the equations that you end up with are going to be a lot worse than this system of equations here. You're actually going to have, what, 2 equations and 2 unknowns, right? In this particular example, that was really easy, but you can see that in general, that would end up being, could be pretty gnarly as an algebraic problem, okay? And in fact, it's not finding the partial derivatives or anything like that. It's not the Calc 3 part that would typically be difficult here. It would actually be solving a system of simultaneous equations that would be the difficult part. Now, what I would typically do for testing for you folks is to have a situation where, these are quite doable, the system of equations. With a little trickery on your part, you should be able to do them. Another thing we are going to do is utilize some technology, including Desmos, though, for some of these problems. Okay? Now, before I go on here and do any more examples or anything, I'm going to talk about a second derivative test for this. Now, I'm going to eventually get around to actually proving this second derivative test, but right now, of course, I just want you to be familiarized with it here. Okay, there is a second derivative test, just like, remember in Calc 1, there was a second derivative test? Well, there is a second derivative test here also to find out whether your point is a local maxima or a local minima, or possibly neither. Okay, there's a different situation that can appear, something called a saddle point also, because we're dealing with higher dimensions here. Let's get to the second derivative test, though. I've got to define something first. There's something called the Hessian matrix, okay? The Hessian matrix I will call H. It is the following. It's f sub xx, reading across f sub xy, and then what? F sub yx, f sub yy. Now, in the situations that we're dealing with, we will be dealing with, we're always going to have all these partial derivatives being continuous, so that what? These derivatives should end up being what from the mixed partials theorem? These will end up being equal, okay? These will end up being equal in the situations we'll be looking at. We won't have any pathological cases where they're actually different, though those do exist, okay? Now, the thing we're really going to be interested in is something we'll be, I guess your book just writes it as D here. D will stand for the determinant. This is actually the determinant of the Hessian matrix. Okay, so there you see I've used vertical bars here. You remember how to take the determinant of a 2 by 2 matrix. It's very easy. It's the product of the main diagonal elements minus the product of the off diagonal elements. Again, this is typically just going to be the square of f sub xy. They're going to be equal. So anyway, okay, this is what I'm going to call D, my determinant of my Hessian matrix, D. Now, here's the second derivative test. Why do I call it second derivative test, right? Well, these are all these are all partial derivatives, and they're second derivatives, right? F sub xx, f sub xy, and so forth. Second derivatives. Now, If D is positive, proceed. Okay? And f sub xx is negative, then at the stationary point, in other words, the potential point you found up here, where the stationary point, by the way, what I'm saying is what? A place where the gradient is 0. That's a stationary point. So let me throw that in. So at the stationary point where the gradient is 0, then you've got a local maximum. Okay? We've got a local maximum. Okay, by the way, let me just mention why this is working here. I could have replaced this by f sub y is less than 0, by the way. That might be an exercise for you. Okay, at the stationary point. The reason why you're getting a local maximum is that this surface, okay, I'll try to make it look surfacey here. Okay, let's say, and this is a high point on the surface here. It's frowning. It's frowning at that point. Okay, f sub xx is concave down. In fact, f sub yy is concave down also. And in fact, with d is greater than 0, I'm going to explain later when my proof here, when I get to it, d greater than 0 is saying all these partial derivatives in every direction, the second partial derivative in every direction, in fact, is going to be negative. This means it's going to be frowning. All this is telling you is that all these guys have the same sign. D greater than 0, that's just a check. All these guys have the same sign. Okay? Now, if D is greater than 0, all the second derivatives will have the same sign. F sub xx is greater than 0. What does that mean? It's smiling. It's going to be going up. Again, this could be replaced by f sub yy. This means it's going to be all smiling up at our point of interest here. And this is going to be a local minimum then. Okay? So this should remind you, it's actually this part, these parts that should remind you of Calc 1. Remember, second derivative test in Calc 1. If the second derivative is negative, you're at a maximum, a local maximum. If the second derivative is positive, you're at a local minimum, at a stationary point. Okay? Now, if D is less than 0, if it's negative, then I'm going to show you you don't have to proceed at all. You can stop. You don't have to examine the other second derivatives. You are at a saddle point. A saddle point is a situation like a saddle, whereas if you look in one direction, the point looks like a local maximum, but in another direction, it's a local minimum, and it's concave up like that. Okay? So the surface is looking something like that at your point of interest here, at your stationary point. Okay, that's a saddle point, like a Pringle potato chip if you hold it. Okay, it's concave up, and at that point in one direction it's concave up, in the other direction it's concave down. Now, do you remember in the second derivative test back in Calc 1, if the second derivative was 0, you couldn't do anything? Okay, well, if D is 0, the second, it was inconclusive. Same thing here. If our cap D, right, our D, don't forget, is the determinant of the Hessian, if that's 0, we can't conclude anything. Okay? We can't conclude anything. Okay? So, inconclusive. All right, let's continue with our example 1 here. Okay? All right, let's look at example 1 again real fast here. Okay, that was this guy. For the potential extrema of this. Okay, so we had f sub x and f sub y. Okay, and we had our original function here. And we had a stationary point. That's where what? The gradient is 0. That's where both f sub x and f sub y are 0. That was at 1, -1. Okay. Okay, so I've just rewritten that here. That's f sub x. There's f sub y. Okay, these, if I differentiate this with respect to y, I get 0. So I've got 0 right here. If I differentiate that with respect to x, I also get 0 there. Notice these are equal. Mixed partials theorem would say they were. F sub y ends up just being plain old 8. Okay, so the Hessian evaluated at 1, -1 is just this constant matrix. Okay, 2, 0, 0, 8. If I take its determinant, I get 16 is greater than 0. That means I'm going to have a local maximum or a local minimum. I don't know yet. Come back here, and let's just double check here. F sub xx at 1, negative 1 is 2. That's greater than 0. Okay, so that means it's going to be what? Concave up everywhere. This guy's, because it's greater than 0, it's going to be the same everywhere. That means it's going to be a local minimum there at 1, negative 1. The actual value of the function at 1, negative 1 turns out to be negative 6. And in fact, this is not just a local minimum. It turns out this is a global minimum. The absolute minimum value of the function is negative 6 at 1 and negative 1. Did you figure out what kind of surface we were dealing with, by the way? Yeah, come back and look at this. Okay, this is a... Right. You figured it out? Okay. I hope you did. All right. Well, look it up if you don't know what it is. Okay? Yeah. All right. Anyway, so I hope you understood that. This is just sort of an introduction to that. We'll look at some more problems soon.